Hello friends, I welcome you in lecture number 10 on complex functions. Our recent topic is analytic functions and we have discussed some examples on analytic functions in previous two lectures. Today also we are going to do some more theoretical examples on analytic functions. So let's start with this example number 7. Show that an analytic function with constant modulus is constant. So if we have some analytic function whose absolute value is constant in some domain D, then we have to show that that function is constant in that domain D. So this question can be asked in this way also. Show that if f of z is analytic in a domain D and modulus of f of z is constant, suppose constant is c at all points in domain D, then we have to prove that f of z is also constant in domain D. So analytic function of constant modulus is always constant in a domain D. So we start by taking f of z equal to u plus iv, and it is given that modulus of f of z is constant, and by the definition of modulus of f of z is under root of u square plus v square. So first we take square on both sides. Mod f of z is c, therefore if we take square on both sides, square of absolute value of f of z is c square in D. In D means at every point z in a domain D, and modulus of f of z is under root of u square plus v square, and we are having square of mod f of z, so it will be u square plus v square equal to c square in domain D or at every point in domain D. So we give this equation number 1. Okay, we will use this equation. Now we are differentiating this equation. See, u and v are functions of x and y, so we can differentiate partially with respect to x and y. So first we differentiate with respect to x. So derivative of u square is 2u into del u by del x by chain rule. Similarly, derivative of v square is 2v into del v by del x, and c is constant, so derivative is 0. Similarly, derivative with respect to y is 2u into del u by del y plus 2v into del v by del y equal to 0. And 2 will cancel out, so we can rewrite in this form u into ux minus v, and also we are using Cauchy-Riemann equations. It is given that function f of z is analytic in domain D, therefore it is differentiable in domain D, and hence Cauchy-Riemann equations are satisfied. We know that CR equations are ux equal to vy and uy equal to minus vx. So we are using these Cauchy-Riemann equations also. So instead of vx, I have written minus uy. Here I am using this equation, second equation. So vx, from this we can write vx equal to minus uy. So it is negative sign here, and 2 is also cancel out simultaneously. And here we are replacing vy by ux. So in second we are using vy equal to ux. So we are converting these two equations. Here partial derivatives are ux, vx, uy and vy. So there are 4 partial derivatives. So we are converting them in 2 partial derivatives of u with respect to x. If you wish, you can write all the partial derivatives in terms of partial derivatives of v also. Here I have converted all these partial derivatives in terms of partial derivatives of u using Cauchy-Riemann equations. So Vx is replaced by minus Uy and Vy is replaced by Ux, and we give this number 2 and 3. Okay, we are going to use these equations. Now we solve these two equations. Here we consider del u by del x and del u by del y as unknown quantities in this equation. So if I want to solve these two equations, I can multiply equation 2 by u. Suppose I want to find out value of del u by del y first. Then here coefficient of del u by del y is v, and here coefficient of del u by del y is u. So if I want to eliminate del u by del y, I will multiply equation 3 by v, and here I will multiply equation 2 by u. Okay, so if I multiply equation 2 by u, I will have minus uv into del u by del y, and if I multiply equation 3 by v, I will have uv into del u by del y, and if I add equation 2 and 3, v into del u by uv into del u by del y will cancel out. Okay, so you can see here I have written taking equation 2 multiplied with u plus equation 3 multiplied with v. So here if I multiply this by u, I will have u square into ux minus uv into uy equal to 0. Similarly, if I multiply this with v, I will have uv into del u by del y plus v square into ux equal to 0. And if we add these two, this will cancel out, uv del u by del y will cancel out, and we will have u square ux plus v square ux, and taking ux common, we will have u square plus v square, and by equation 1 we can replace u square plus v square by c square. So we obtain c square into del u by del x equal to 0. Now we try to find out del u by del y. So we have to eliminate these ux terms. So here coefficient of ux is u, and here coefficient of ux is v. So now we will multiply this equation by v and multiply equation 3 by u, so that I will have uv into del u by del x, and here also I will have uv into del u by del x. So we multiply equation 2 by v and equation 3 by u, and we subtract this equation number 3 from 2. So we obtain this type of equations. Now again this uv, this is this one, 2 into v minus 3 into u. So 2 into v. So if we multiply 2 with v, then this will be uv del u by del x, and this term will be uv del u by del x. So it will be cancel out, and this is going to be minus v square uy minus u square uy. So that I have written minus v square uy minus u square uy, and if we take negative side on right hand side and take del u by del y common, we will have u square plus v square into uy equal to 0, and by equation 1 u square plus v square is c square. So we obtain c square into del u by del y equal to 0. Okay, that is given to be number 5. This is equation number 4, and this is equation number 5. Now this c is constant, mod f of z equal to this c is constant in a domain, it is some real number. So there are two possibilities, either it is 0 or non-zero. Now suppose this constant c is 0, then by 1 we will have u square plus v square equal to 0. If c is 0, then u square plus v square equal to 0. So if c is 0, by 1 u square plus v square equal to 0. Now u square and v square are non-negative functions, so this is 0 if and only if u and v both are 0 at every point in a domain D. And if u and v both are 0, then our f of z is u plus iv. So if u and v both are 0, then f of z will become 0 at every point in domain D. This means f of z is constant in a domain D. So if c is 0, then by 1 we obtain this. Now suppose c is non-zero, then from 4 and 5, if c is non-zero, c square is non-zero, and here multiplication of c square in del u by del x is 0. So if c square is non-zero, we must have del u by del x equal to 0. Here also, if c square is non-zero, we must have del u by del y equal to 0. Therefore, if c is non-zero, we can say that by 4 and 5, del u by del x is 0, del u by del y is 0. So partial derivatives of u are 0 at every point in a domain D. And by Cauchy-Riemann equations, we can write del u by del x equal to del v by del y. And del u by del y is minus del v by del x. So this is 0, therefore vx is also 0. So all the partial derivatives of first order are 0. The partial derivatives of u and v of first order are 0 at every point in a domain D. That implies that f of z equal to u plus iv is constant in a domain D. Because if partial derivatives of u and v are 0, then u and v are constant functions. Therefore, f of z is also constant function. Next example. It is given that f of z is a regular function of z. Okay, we have discussed that another name for analytic function is regular function. So sometimes they ask in this way also. Instead of analytic function, they can write regular function, or another name is holomorphic function. So it is given that f of z is a regular function of z, and we have to prove this. Del square by del x square plus del square by del y square of modulus of f of z square equal to 4 into modulus of f dash z whole square. So first we find out the expression for this in terms of z, because we are applying this to the function of z. So first we simplify this, or we obtain some expression for this del square by del x square plus del square y by del square in terms of z. Therefore we start by taking z equal to x plus iy, and if we take conjugate of z, it is x minus iy. Now if you add these two equations, you will have z plus z bar equal to 2x. And if you consider z minus z bar, then you can see x will cancel out, iy minus minus plus iy. So 2iy z minus z bar. So from this I obtain x equal to z plus z bar upon 2, y equal to z minus z bar upon 2i. Okay, so these are the formulas for real part of z and imaginary part of z. Now by chain rule, we have this expression. Okay, this is by chain rule. Partial derivative with respect to z is nothing but partial derivative with respect to x into del x by del z plus partial derivative with respect to y into del v by del y by del z. Now x is z plus z bar upon 2. So from this we obtain partial derivative of x with respect to z is 1 by 2. Similarly, partial derivative of y with respect to z is 1 upon 2i. So these values are written here. Del x by del z is 1 by 2, del y by del z is 1 upon 2i, and del by del x and del by del y, these two remains as it is, and we put values of these two. So therefore del by del z is 1 by 2, value of del x by del z from this is 1 by 2, del by del x plus del y by del z will be 1 upon 2i, that is 1 upon 2i is written in place of this into del by del y, partial derivative with respect to y. Now 1 upon I, or we know that I square is minus 1, therefore we can write minus I equal to 1 upon I. So 1 upon I is replaced by minus I, and this is del by del z equal to 1 by 2 del by del x, and 1 upon I is replaced by minus I, so it is minus I by 2 del by del y, and this we can rewrite as by taking 1 by 2 common, we have 1 by 2 del by del x minus I into del by del y. So this is partial derivative with respect to z, and using chain rule we are converting it in terms of x and y. Similarly, we can use chain rule to write down the partial derivative with respect to conjugate of z, that is z bar. So this is also by chain rule. Del by del z bar is nothing but del by del x del by del y, and here partial derivative of x with respect to z bar, here partial derivative of y with respect to z bar. Again del x by del z bar, partial derivative of x with respect to z bar is 1 by 2, and here it will be, here also it is 1 upon 2i. So we have to put those values there. Del x by del z bar is 1 upon 2, del y by del z bar is minus 1 upon 2i. 1 by 2 can be taken outside, so this is del by del x plus I into del by del y. Now we consider multiplication of 1 and 2. This is number 1, this is number 2, and we will write this right hand side in that expression. So from 1 and 2, if we consider multiplication of left hand sides, we have del partial derivative of del with respect to z and z bar, and if we multiply these two, then you will have 1 by 4 del square by del x square minus I square into del square by del y square, and I square is minus 1, so it is going to be del square by del x square plus del square by del y square. Okay, we are using the formula that a minus b into a plus b equal to 1. So this implies del square by del x square plus del square by del y square, and 4 is taken on the left hand side, and this we can rewrite as 4 into del square by del z bar. So you can see del square by del x square plus del square by del y square is converted in terms of z, it is 4 into del square z by del z bar. So we will replace this by that function of z. So in the next step we write, we start by left hand side, mod f of z square, and this we replace by, this is replaced by 4 into del square z by del square z del z bar. Now here we are using the property that mod z square is z into z bar. So therefore instead of z we have mod f of z, so it is f of z into conjugate of f of z. Now here we have to first take partial derivative with respect to z bar. So first we write in this way, 4 into del by del z and del by del z bar of f of z into this. So first we consider, and here we are interested in first partial derivative is with respect to z bar. So del by del z as it is, and del by del z bar, this we have to write in this way to understand. And here with respect to z, so f of z into f of z bar or conjugate. Now this is derivative with respect to z bar, so we will consider f of z as constant. So it is f of z into del by del z bar of f of z bar. Okay, this step is, you can understand in this way: 4 outside, del by del z of del by del z bar of f of z into f of z bar. Now here derivative is with respect to z bar, so we consider f of z as constant and partial derivative of f of z bar with respect to z bar. And also we are using this fact, f of z bar is nothing but f of z bar, conjugate of a function equal to function of conjugate. So that property is used here. Instead of writing conjugate of f of z, they are writing del by del z bar of f of z bar. Now this is not partial derivative. Here I have to write ordinary derivative because it is function of only one variable. So d by dz bar of f of z bar, this I can write as f dash z bar, and this is f of z. Now here we have to again take second derivative. This is simplification of first derivative. Now if we consider this, we have written as f of z into f dash z bar. Now suppose I want to consider partial derivative with respect to z, then in f dash z bar there is no z, so it is outside, and we have del by del z of f of z, but z is function of only one variable, so instead of del by del z we will write d by dz of f of z, that we can rewrite as f dash at z bar. So therefore, and again we are using this property, f dash of z bar is nothing but conjugate of f dash of z. So conjugate of f dash of z into conjugate of f dash z, that is going to be f dash z modulus square. So in this way we can do many problems on complex analysis and analytic functions as per particular session. So analytic functions are very much important functions. You can use Cauchy-Riemann equations to decide their analyticity. So I hope you like this lecture. Thank you very much.